Okay, so hello and welcome to this video tutorial for Engineering Mechanics Statics by R.C. Hibbeler, this textbook here. So we have this problem from chapter 2 of the textbook that states, determine the magnitude of the resultant force acting on the corbel and its direction theta measured counterclockwise to the x-axis. So if you've done all of the fundamental problems up until this point, you'll notice that this is a very simple problem. Let's go ahead then and start off by sketching our free body diagram. So we've got this 600-pound force here. We've got this 400-pound force here. We've got this 700-pound force here. Let's add some geometry to this sketch. We can add our x-axis here. We can add our 30-degree, this 30-degree angle here. We've got this 3, 4, 5 triangle here. Let's just add the magnitudes of our forces as well. So this is 600 pounds, this is 400 pounds, and this is 700 pounds. Okay, I believe we've got everything we need in this free body diagram to move ahead. So we can start by resolving horizontally. We can say that the sum of the horizontal components here, we've got 3/5 of 600 acting to the right, and we've got 700 sine 30 acting to the left. And when we bung this into our calculator, we find that this is equal to minus 246.2. Let's move on then and resolve vertically. So we can say that the sum of our y components here, we've got 4/5 of 600 acting down. We've got 400 acting down, and we've got 700. Oh, apologies, I've just noticed I made a mistake earlier. I should have said cos 30. Cos 30, okay. So 700 sine 30 acting down. And when we bung this into our calculator, we find that this is equal to minus 1,230. Okay, so what this is telling us then about our resultant force is that it's acting 246.2 down and 1,230 to the left. Sorry, I've just got them the wrong way around. It's acting 246.2 to the left, since that's its horizontal component, and 1,230 down, since that's its vertical component. Let's go ahead and diagrammatize this then. So we can say it's acting 246 to the left, and we can say it's acting 1,230 down. Let's just add these magnitudes. So 246.2 and 1,230. So we then want to determine this magnitude here. If we want to do that, we can go ahead and use Pythagoras' theorem, which would look like this. We can take the square root of 246.2 squared plus, that's an odd looking plus symbol, 1,230 squared, which when we bung in our calculator, we find is equal to 1,254.4, which we can add to our diagram here. Okay. So the final part of the problem here is asking for the direction theta measured counterclockwise from the x-axis. So note that this angle that it's asking for really, it looks something like this. So if I were to add the x-axis to my sketch here, let's add the vertical axis here. What it's really asking for is this whole angle here, right? So it's not, maybe some students might make the mistake of just determining this angle within the triangle, but actually note that we need to add 180 to it, okay, which won't be that difficult. Let's go ahead and solve for this angle inside the triangle first then. So students will know you can use any trigonometric ratio you like here, sine, cos, or tan, since we have all sides of the triangle. let's just go with tan. So we can say that the tan of theta, where theta is the angle inside the triangle here, is equal to the opposite of the adjacent, where the opposite is 1,230 and the adjacent is 246.2. We can then say then that theta is the inverse tan, taking the inverse tan of both sides here, of 1,230 all over 246.2, which gives us a value of 78.7 degrees. When we add that to 180, we find that's equal to 258.7 degrees. And there we have it. So the solutions to this problem here will be this 1,254.4 magnitude here, which we really should give its unit, pounds, and this 258.7 degrees counterclockwise from the x-axis. If you have any questions or comments about this problem, please feel free to leave them in the comments down below. Otherwise, thank you very much for watching.